And that's not the one that I had. This is just a general logistic regression curve. And something to notice about this. So I have my probability on my y and my difference on my x-axis. And that difference, I did the difference between the favored team's ranking and the non-favored team's ranking. So that difference will always be positive. So when I show my graph later, it'll just have this side, because the difference is always positive in my whatever. And so one thing to notice is as the difference increases, the probability of that team increases, which makes sense because if the team is, if there's a big gap in between the two teams, the probability should go up. Another characteristic that's interesting is that this point 0.5 says that if a difference between two teams is 0, meaning they have the same score, then each team has a 50% chance of winning, which makes sense. Okay, so this is the general logistic regression model. It models the natural log of the odds of winning a game, and it equals it to a linear function with an independent variable, which my independent variable is the difference between the two. And you do some not so fun algebra to solve that for p. You get a probability function which looks like that. And luckily, Minitab, it does that for you. So my Minitab, I had the higher team's ranking, had the lower team's ranking, had the difference, and then I had a 0 or a 1 to say if it was a 1 if the favorite team won, it was a 0 if they didn't. And so that was the output, and the graph looks like this. We've got a lot of stuff going on here. So first off, this red line is the best fit line. This red line is the best fit line off the data that I had. And I have a 95% confidence interval with the green dashes right here. And I've got all these blue dots, which there's actually exactly 441 of them, which means there's a lot right here and a lot right there. 441 is the number of games that were played in those 7 years. So it goes, you got the difference here, and if it was a 0, it's down here. If it's a 1, it was up here. So luckily I have most of them up here. It's actually 74.7% to be exact. And I have some outliers here, and I have this one, which is just ridiculous. We'll get to in a second. But I pretty much figured out that with not counting those, which this is 3, and then that's 1. So without counting those 4, you've got pretty much, when you've got a greater team that's got 10 and out, they're going to win. And so I decided to look at these outliers. And I had New Mexico and Harvard this 2 years ago. Yeah, 2 years ago. What was a 14.6 difference? The next one was a 15-point difference, and a almost 17-point difference. And to put that into perspective, they're not only like mathematical outliers, they're also, I guess, ESPN basketball outliers, because the headlines of these articles were Pool's enormous upset, and I think this one is shocks and stuns is the next one. So it's not only mathematically crazy, but in real life it's crazy as well. And then I'll go back to this one, which this is almost 32 difference, or 32 points different than in between the favorite team and the non-favorite team, which is twice as much as these right here. So it's like, what game is that? And so this is a number 2, Missouri versus Norfolk State. Does anybody know what that is? Anybody ever heard of that? I never heard of it. Have you? Virginia. Norfolk, Virginia. Dr. Anderson. Okay, so 32 points different, which is just unheard of. And they look happy. So that was in 2012, and Norfolk State was actually a 21-point underdog. They're 31 points different in mine, but in real life, a 21-point underdog, which is ridiculous. They ended up winning the game by 2, 86-84, and this guy right here, he had a quote afterwards, and He said, "Well, you even messed up my own bracket." So he didn't even think they were going to win. So I thought that was really funny because, I don't know. Okay, so I took the 441 games. I did the binary logistic regression and solved and got this. That's not what I'm doing. So I got this number. This is mine, 74.7, compared to 73.8, 72.4, and 71.9 of the others, which mine theoretically should be higher because I'm looking back and I'm adjusting the formula so that it will be higher, but it's still cool. So my first question was, are the systems adequate in projecting games? Like, are those percentages high enough with that amount of games to be adequate? And so I did a hypothesis test with one sample proportion, and I used the lowest ranking one. Well, hang on. Yeah. So my null hypothesis would be that p is a half, and then my alternative is that p is greater than a half, hoping that it would be greater. Because if it's not, then we're in trouble. But okay, so I used the lowest one, which was 71.9%, because if that one's adequate, then the ones that had higher percentage would be adequate as well. So you subtract hypothesized value, p1 minus p, they're the same because they're both a half, divided by the number of games. I got a z-value, and then my p-value related to that z-value is really small, which is good. That's good. It means we can reject the null hypothesis, and we can accept this, which was what we wanted. That means that our systems are adequate. So then, since I did have quote unquote the best one, I did a hypothesis test to say, is there a difference between them? Is 441, is that enough to say there is a difference? And with that, I did another hypothesis test with two sample proportions, which I compared the highest and the lowest. And because, if there's a difference there, or if there's not a difference there, then the ones in the middle, then there's not going to be a difference in those two. So I went through my null hypothesis was that they are equal, and my alternatives are not. I went through the same process, instead of different numbers, obviously. I got a p-value that is not small. Talking about hypothesis test. So in that case, we'd fail to reject the null hypothesis, which means that there really isn't a difference. I think Dr. Wesley on that part of the paper, he said, that's unfortunate. It is.
Yes.
I wanted mine to be the best. But, okay, so back to this ESPN bracket challenge, which, I'd like to win $1 billion from Warren Buffett, but nobody's ever going to do that. So, ESPN bracket challenge is a tournament thing that ESPN hosts every year, and you get points based on wins and how deep your brackets go. And the prize for this is $10 grand and a trip to next year's championship game. So it's not $1 billion, but it's still worth playing for. And the trick is that in the bracket challenge, you have to project all of the games before it's even started. So you can't go game by game and know who's playing. You have to project everything up front. And so it's crazy. I have a screenshot from my bracket 2 years ago, I think, just kind of illustrate how it works. So this gray area right here is the games that are already scheduled, meaning they are scheduled. And then all these right here are my picks, and there's a lot of red, but I wanted to illustrate that. This is a bad section. So this first round, for every green, I got 10 points, and the second round, for every green, I got 20. So the points increase every round because, like I said, this Indiana game, I had to choose that Indiana was going to go this far before Indiana even played this game. So you get more points per round. And so I was trying to, base my formula on not really paying attention to the first couple games and trying to win the games that were deeper, because I lost this game right here, which means I don't gain 10 points. But losing this one right here means I don't gain 40. So it's more important to kind of pay attention to the teams that have a chance of making a deeper run than kind of, spending hours trying to figure out who's going to win between NC State and Temple. So with that, I did my formula against for the bracket challenge for the past 7 years, like I said, 2008, 2014. And I have rounds, there's 6 rounds